All right, so in this video, we're going to take a look at injective linear transformations and something called the kernel, which we'll define in a second. Before we do that, I do want to talk briefly about something called a preimage. So a preimage is something defined like this. Okay, where we have our linear transformation. All right, so the way we would state something like this is the preimage of, for each v, we define the preimage of v to be the subset of u. Right, so here one thing to realize here when we talk about a linear transformation, we are talking has a domain of u, linear vector space u, and a codomain of v. Okay, now the preimage are vectors that are in u, right? So T inverse v is an element of the vector space u. Okay, all right. And what this statement is telling me here, it's asking for, all right, if we have here an element in u, right, when I take the transformation, that it goes to v, right? So in general, what we're looking at are these preimages. So we're looking at a specific vector in our codomain v, and the preimages are all the vectors that get mapped on or do the linear transformation that go onto v, right, from our codomain, from our domain vector space u. So u1, u2, okay? So sometimes there may be more than one, sometimes there's exactly one, right? And sometimes there's none, right? And those apply to different types of situations, different types of linear transformations, right? So the preimage might be empty for a particular vector. Not to say zero, right? That is different, right? In fact, we can think of one preimage that we know is the zero vector. So I know, since it's a linear transformation, the zero vector in u always maps onto the zero vector in v, right? So the preimage of the zero vector in v, right, will always include the zero vector, right? So it's the zero vector in u. So it's a u element of u, right, such that t of u is equal to the zero vector, right? So we know for a fact that the zero vector in u is definitely an element of the preimage of the zero vector in v. All right, now this may be the only element, right? For sure it has this one, but there may be more, right? And then later we'll come up with reasoning as to well, what if it has more? What can I conclude about the linear transformation? Now this is all a setup into talking about what are called injective linear transformation. So here, so you want to define here an ILT, right? Something called an injective linear transformation. Okay, so the definition is as follows. All right, we have a transformation from vector space u onto vector space v, and we say it is injective if distinct inputs always produce distinct outputs. All right, so what that means here Excuse me. Okay, so what that means is that T of U1 is equal to T of U2. If this is true, then U1 must equal to U2. All right. Or equivalently, all right, so this is the statement and something called the contrapositive. If we negate the conclusion, if U1 does not equal U2, then T of U1 does not equal to T of U2. All right, so these two statements are equivalent, right? This statement and this one, right? Logically equivalent statements. All right, the second one is what's called the contrapositive, where we negate the conclusion, in this case, U1 not equal to U2. And that implies the negation of the hypothesis, T of U1 does not equal to T of U2. All right, so showing either of those is equivalent, but really what is going to come down to, as we'll see, is trying to determine what is in the kernel of a linear transformation. So let's define that. Right. Now so before actually I move on to that, the way to think about injective in terms of maybe an algebraic function, think of that as like a one-to-one property. Right. If you have an input, right, it leads to a unique output. All right, now the kernel, I want to define KLT, right, the kernel of a linear transformation. So we define the kernel of T is, so we use this notation, K of T is an element in the domain such that T of U is equal to the zero vector. Okay. All right, and again, this is in V. All right, because that's where the codomain, that's where the transformation maps vectors onto. All right, so here, as you notice here, this is a preimage, right? It's just for a very specific vector, in this case, the zero vector. Okay, so so what we have here is that the preimage of the zero vector is what defines the kernel, right? The kernel is always a subspace of the domain of U, right? You can verify by verifying those three properties of a subspace. I know it's non-empty from a previous theorem, where I know the zero vector in U maps onto the zero vector in V. So I know it contains at least one element. And you can prove here, it's closed under addition, closed under scalar multiplication, etc. Right? Now, if I know the matrix of a linear transformation, well, it just boils down to really finding the null space. Right? Now, if you find this, all right, so we can classify the kernel of T to be equal to the null space of A. All right. Okay. Okay, so really what you are after here is you want to show that it comes down to solving either some kind of homogeneous linear system, right? If you're mapping between two vector spaces, right, what you want is you want to set up this equation, right, and solve and determine what those solutions are. Okay, so in terms of injective, what it boils down to is to finding the kernel. And this is what theorem KILT states. So this theorem states T is injective if and only if the kernel of T is equal to the zero vector. Okay, all right. Okay, so now the reason why this has to be the case here, let's think here. So if and only if, right? That's what this means here. If and only if. All right. Okay, so what this means here is that it goes in both directions, right? It's an equivalence relation here. So if T is injective, then let's say that for just kind of a sketch of a proof. So for the first direction, we'll prove T is injective. So let's say there exists a vector U that is equal to the 0 vector. But I also know that the 0 vector of U also maps onto the 0 vector of V. All right, but the fact that it's injective means that these vectors need to be equal to each other. So the U vector is actually the 0 vector of U. So the kernel of T can only contain the 0 vector. Okay? All right. In other words, when this is the case, when the kernel is only containing the 0 vector, we say that it is a trivial kernel. Right? Same like a trivial null space. It is analogous there. So that's the first direction. Now in the other direction, let's say T, the kernel of T is trivial. So here, K of T. So we assume this. Okay, so that means that T of U1. So let's do our proof here. And let's say that T of U1 did equal to T of U2. All right, and here, by subtracting but T of U2, we get the 0 vector, again in V. All right, and by linearity, because we are dealing with linear transformations, this must be true. Okay, so that means that this vector U1 minus U2 must be in the kernel of T. But I know there is only, by assumption, I know there is only one element in the kernel of T, and that is the 0 vector. So that means that U1 must be equal to U2. Hence, it is an injective linear transformation. Okay, so this is going to be our main computational check, right? If we're given a linear transformation and we're asked to determine, is this an injective linear transformation? Well, it comes down to finding the kernel. If you have the linear transformation in terms of a matrix, then it comes down to finding the null space. And is it the trivial null space or the trivial kernel? If you have proven that, shown that somehow, then it is injective, right? So that'll be our computation here.